Hey, folks, we'll get started. Thanks for joining. I think one request, if you haven't listened to our recording of lesson 9, I'd encourage people to go back and listen to it for without that context, at least the early part of the lecture where we go through what Jeremy covers in lecture 10 would be somewhat of a quick or abrupt introduction. So I posted the recording in the Slack channel of this course for the study group. So I'd encourage all of you to listen to it. It also has the video, I believe, so you can follow along on the slides that I used to talk about it. With that, let's get going on lesson 10, which is, I think, titled Deep Dive into Stable Diffusion. Basically, it's still a high-level introduction to the components that make up stable diffusion. So I believe folks should be able to see my screen now. Could one of you acknowledge that you can?
Yeah, we can.
Okay, great. So we have kind of a full agenda. Probably take an hour and a half to us to get through all of the material because I think I've prepared not just Jeremy's lecture, but also the lecture corresponding to 9A, which is Jono Whitaker's kind of walkthrough and his notebook. And we'll go through all of that today so we can get a good idea of the major components of stable diffusion and the role they play in the algorithm. Of course, not every line of code, but just a high-level understanding. The rest of the course is to build up the code for stable diffusion ourselves from the ground up. That will start next week, and we'll discuss that as we go through the rest of the course. So just a couple of slides on revising what we went through last week. Jeremy used this very simple example of MNIST digits, encoded MNIST digits, which are then passed into the backbone of the stable diffusion algorithm, which is essentially the UNet. And as we saw in the math of diffusion portion of last week's lecture, due to some mathematical simplifications and 1950s discoveries in math, essentially a forward process, which is the training process for stable diffusion, where the unit predicts or part of what happens there in the forward process is addition of noise. In the inference process, what happens is or what is referred to as the backward process, is where we provide the noise and ask the unit to infer and repeat through that loop a number of times. And those, as we discussed last week again, are referred to as the time steps, although there is no rhyme or reason why they are referred to as the time steps. It just is an unfortunate carryover from the ODE type of equations that were used to originally explain the math behind diffusion. But what this picture shows is essentially if you can one hot encode the digit, add some noise to it and pass it to the unit, and then the unit is used to predict the noise. And prediction of the noise is referred to as the score function, because that's the indicator, if you will, of how the unit is doing, and it predicts the noise. We then multiply that noise by some value, much like a learning rate, some constant value, and then subtract that from the input, do that a number of times, and we can extract the image that we are after, which would be the digit 7 in this case. And we are, in this explanation, kind of ignoring the compression that happens and the latent space that we operate in typically in order to reduce the computation needs. So if we then, this is like explaining in 2 minutes what took 2 hours to explain last week. So that's the reason to encourage people to go back and listen to that lecture. But the key components
Also,
is to
yeah, I was
go ahead,
saying,
Mike.
oh, yeah, also a difference between the unit and the auto encoder, in which the latents versus the that thing, uh, the natural image, in which we had some difficulties in understanding.
Yeah, that I it will become very clear as we go through the notebooks and so on today. So,
Okay.
and in fact, it kind of explained in this slide, but even more so as we go through the notebooks that I'll take you through in the rest of this lecture. It will become abundantly clear of where does the VAE play a role and where does the unit play a role. So by the end of this lecture, hopefully there ought to be no confusion of what role at least each of these components play. Doesn't mean we'll be able to code each of the pieces ourselves, but which we'll accomplish throughout the course, but we'll at least not have any confusion about where is the unit and where is the VAE and what roles they play in as part of the stable diffusion. But right here is an explanation of kind of the key components, if you will, of the stable diffusion. So the unit is kind of the backbone. The unit and each of these three components, what are its inputs and what are its outputs? So the unit is often referred to as the backbone of stable diffusion. Its inputs are, now we are talking about latent diffusion, and the reason it's called latent diffusion is because the inputs that go into the unit are, and again, this is during training, okay? And then during inference, we'll see as we go through the rest of the lecture what happens during inference, which is what we often use the stable diffusion for. But remember that there is a training piece that goes into stable diffusion as well, after which we can use the stable diffusion for inference. So during training, what goes into the unit backbone are somewhat noisy latents, that is noise added to latent images. And that's why it's called latent diffusion. And what the latents are is something we'll again talk about in a second. What comes out of the unit is the prediction of the noise, which is part of these noisy latents. And what we do as part of, there's a component of the stable diffusion that's not referred to here because it's kind of an iterative process, and that is the scheduler. And we use the scheduler to repeatedly subtract some amount of noise multiplied by a constant. The amount that's subtracted out is the noise that's predicted by the unit. So that's why you see this minus sign. So you can imagine a loop going through the unit repeatedly with it predicting the noise, and then some constant of the noise subtracted from the latents and repeatedly, right? And that happens during inference. During training, actually, the noise is added, the noise is predicted, and so on. Each of these, what I'm describing, we'll go through the notebook and look at it in greater detail. The role of the VAE, which is the variational autoencoder, is twofold. If we are using it in training, then it's used to generate the noisy latent. So it's the, or I should say, it's used to generate the latent. So what happens is the VAE's encoder, in case of training, is what is used to generate the latent. In case of inference, the VAE's decoder is used to, after we have gone through a series of steps and extracted the latents and separated the latents from the noise, in case of inference, then those latents are input into the VAE's decoder, and what emerges out of the decoder is the large image. So this is where the unit operates in the latent space, whereas after the latents are provided as input to the VAE's decoder, what emerges out of the decoder is the pixel space large image. So for example, we would get a 512 by 512 by 3 image coming out of the VAE decoder. What goes into the decoder could probably be something of the order of 4 by 64 by 64 latents. And we'll, again, as I keep repeating, we'll see the specifics, the sizes, and all of those kinds of things as we go through the notebook. The clip text encoder is what is used to convert the textual input that we provide. You know, we want an image of a puppy or image of a cat or a dog or whatever, or, you know, astronaut riding a horse, for example. The clip encoder is what is used to convert the text that we provide, the text input, into an embedding that is then combined or that's then sent into the VAE encoder, which then generates the latents in case of training. Right? And in case of inference, it's again sent into the unit. So essentially, we have three components in the latent diffusion model, typically, along with a scheduler. The unit, which has these inputs, a somewhat noisy latents, out comes the latents. Then a VAE decoder when we are doing inference, the output after going through a series of these reduction steps, out comes the latents from the unit. The latents which are smaller, therefore more economical in terms of compute, out comes the large image from the VAE decoder. And the clip text encoder is what is used to guide the process so that we get the relevant image that we are seeking, but it is essentially used to convert the text that we input into an embedding. And as I mentioned, the output of the unit, which is often referred to as the noise residual, is what is used to compute a denoised latent image representation, and that's done via a scheduler algorithm. Okay, and this will, again, it's kind of a lot of words, but we'll see the details a little bit in a little bit. The clip embedding is trained through this contrastive loss. That's what the CL in clip embedding stands for. So as we saw last week, you take a bunch of images from the internet, you have the alt text description of them, and you train them jointly through the process to generate clip embeddings. And what we want is anything in the diagonal to have a high value and anything not in the diagonal, because the diagonals is what correspond the text to the image. Therefore, as we saw last week, anything which is a beautiful swan, a graceful swan, a lovely swan, and so on will tend to produce images corresponding to a swan, and so on with respect to these various titles. So this is what we use in order to generate clip embeddings, which are a way to train or generate embeddings. And again, we'll look at this process in greater detail and, as well, will generate the desired image out of our stable diffusion algorithm. What Jeremy does then is to, in the next several slides, I'll just take you quickly through a couple of papers that Jeremy talks about, again, more at a high level at this stage of the game, not in details. He just wants us to get familiar with reading papers as part of the course. And in fact, in lecture 11, if you go through that, he kind of takes us through an example paper of how he tends to read papers. But here, the point is he's trying to explain what happens during stable diffusion inference, and then how the process has been accelerated with some papers that appeared late into 2022. Keep in mind that this course was starting in October 2022, so these couple of lectures were given in that time frame. It's already been 9 months since then, and a lot of progress has taken place in this particular domain. So what he is pointing to here, and we'll see this in the notebook that we'll go through shortly, is a process by which somebody has generated an image of Jeremy Howard smiling, if you will. And this is using stable diffusion algorithm to, in an inference manner, or using the inference part of the stable diffusion algorithm. So the analogous steps, if you will, are taking a 1-hot encoded MNIST digit like 3, adding a bunch of noise to it, using the unit to predict the noise that's part of this combined image, subtract the noise repeatedly from the input image, and what's left is the latent portion of the image. And of course, if we want to do the compression decompression and have this unit operate in the latent space, then we would have a VAE decoder, which will then take the input of this eventual denoise latents, and out will pop the image 3. That's essentially what is happening here. We start with a completely noised latent, pass it through, and here he has kind of taken us through the various steps. As he mentions in the lecture, this ought to be 60, because I believe he, the particular inference algorithm took 60 steps to generate this denoised, decoded through the VAE, full 512 by 512 by 3 image of Jeremy Howard. The interesting part is the fact that originally, when this algorithm was developed, maybe I believe it was around 2013 or 15 or something in that time frame, it took about 1,000 steps to get from the noise all the way to the emergence of the desired image. Over time, the acceleration of this process has taken place, and there's been tremendous speed up and in generating the desired image. Therefore, also a reduction in the number of steps that are needed to generate that. And the paper that he refers to in that, and in fact, there's even a walkthrough of the paper by John Whitaker, who is one of the co-lecturers, if you will, of this course. And I'll point to it in a second, and you can go listen to the paper walkthrough of that if you're interested in the details of the paper. Here, we'll just kind of brush through or conceptually understand what the paper is attempting to do in the next couple of slides. So if you want a lot more detail on it, it's better to go through the paper walkthrough. But the paper is called Progressive Distillation of Fast Diffusion Models. And what it is, as the title itself says, it is an attempt to apply distillation. And distillation, many of you may already know, is one of the techniques in deep learning where a fully trained, highly complex, lot of parameters teacher model is used to train a student model, which is a small, computationally more efficient, less parameters, but generating close to what the teacher model can generate. So this process of training a student model using a much more complex teacher model is what is referred to as distillation. So what the progressive distillation talks about is the process of utilizing a distillation process to train the unit to be able to jump steps throughout this inference process, so that, for example, we could, in this particular example, he's talking about, let's say we take image which emerges out of this scheduling process that we talked about, of repeatedly subtracting the predicted noise of the unit from the input, which has both the noise and the latency. Then what we desire is to go from step 36 Jeremy Howard to step 54 Jeremy Howard, for example. Let's take that as an example. Then what he's saying is, look, it ought not to be that difficult for a model, for a neural network model, whose input is this desired, whose input is this noisy latent image 36, and whose output is this noise removed, output image 54. So we could, in this instance, it's Jeremy Howard. We could use the swan. We could use the logo, FastAI logo. We could use a bunch of images and generate the image at step 36 and at step 54 and train this unit using an MSE loss, for example, to just go from 36 to 54 in a single step. And by repeatedly applying this kind of a concept, the progressive distillation enables a much faster extraction, if you will, of the desired image through the inference process. And that's essentially what conceptually the progressive distillation paper is all about. So that's kind of what he's explaining in the next couple of slides. I just threw in a slide of what conceptually what a distillation process diagram, if you will, or the key portion of a distillation loss and how a teacher model is used to train a student model in distillation. So essentially what we do is take the input. The teacher model is already trained. It's fully trained. Think of it as, you know, the original network that has been trained for the purposes that we are using it for. It's a large model. It has a very high number of parameters and it generates labels. Now, what we then do is try with a simplified or a much reduced model, the student model. We use that to generate the predictions on the same data which is input into the teacher model. The teacher model gives us some labels. The difference between them is used as one of the components of the loss, and that's referred to as the distillation loss, multiplied by a constant, some constant that we give a value of it as beta. Then the actual predictions of the student model are also compared to the ground truth labels, which we know of, and the difference between the ground truth predictions and the predictions that the student model gives of the input are also compared, and that loss is used as a student loss multiplied by alpha. Combine these, that total loss, we go through and train this, and after we have kind of optimized this particular structure, we get out a student model which is much smaller, much more computationally efficient, and almost as good as the teacher model. So that's kind of, if you will, a 2-second explanation. There's a lot more details. You can look up papers on distillation and how that is used to train a student model based on a much more complex teacher model. So essentially what he explains in the next slide is the fact that what is done in the progressive distillation paper is they first train a student model to predict a couple of steps. Then, therefore, the input is given. We have a teacher model which has been completely trained on the whole process. It's capable, but it's a much larger model. And what is then done is using the distillation process, a smaller student model is trained, and that is used to predict, let's say, 2 steps of the inference process. That is, the input to it is, let's say, step 0, and out comes step 2. Right? So we add the noise and we get the student model of step 2. Then what we do is we may generate a copy of that student model and give it input 2, take it through 2 steps, or to 3 and 4, and then train a new student model which is able to then predict the step 4. And repeatedly, by going through these kinds of, each time creating a copy of the student model and then enabling it to predict and taking 2 steps through that, we eventually come up with a student model which is able to significantly reduce the number of steps that are needed in order to get from all noise to the final image that we seek. Again, as I mentioned, if you want a much more detailed explanation of all the things that are done with progressive distillation, you can refer to the progressive distillation paper walkthrough of diffusion models that John Whitaker, who is the person pictured here, takes you through. So this video, I'll post a link to that. It's available as part of the course information as well that you can go through. The next couple of slides, actually the next slide just says, not only is the student trained to predict the initial steps, so going from say 0 to, in this case, he jumps to say step 12 and then another step 12, 24, but it's also used to predict the later steps, not just the initial steps. And this progressive distillation paper talks about how they go about training such a student model, how they use the distillation process in order to speed up the steps that are needed to get to the model that we seek, starting with pure noise. So that's what that is about. If we were to add in what we'll again look at in the lecture and as we go through the notebook, this is a process we touched on last lecture. This is classifier-free guided diffusion with some settings. Apologize for this. I just cut and pasted from the YouTube images, but these are values like 2, 3, or 2, 6, 7, 12, various values that we set the classifier-free guidance parameter to be. And typically, if we are using classifier-free guided diffusion models, then as we'll see in the notebook, we provide 2 inputs to the textual clip embedding portion of the network that I talked about, the clip embedding part, which converts the text to embedding. One is if our desired image is that of a cute puppy, we provide the cute puppy, but we also start with a null input as a reference. So we provide cute puppy and the null input, take both of them through the clip embeddings. So we'll have 2 embeddings and we provide 2 values through the unit, and the unit therefore predicts 2 outputs. Those 2 outputs are combined in some way, and again, the details depend on how the particular stable diffusion or diffusion process is implemented. You could just combine them, do a weighted average of them, and that is then input as the next value for, or I should say that combined value is what is sent in during the next step that we take with the unit. So the cute puppy is always the same thing that's sent in, but as we step through, we send in the combined values, and that combination is a combination of the output of the unit. Right? So that's what is done when we talk about classifier-free guidance, and classifier-free guidance helps us get the desired image, that of a cute puppy, as an inference output from the network much quicker. And so the student model, which is generated as part of this progressive distillation, is also provided, as you see here, not just the noise and the prompt, but also something called the guidance scale. And the guidance scale is the setting of the value of the guidance, which is just an integer of certain value. And we get to play with this and see what impact setting the guidance scale has on how quickly or how badly the image that we desire emerges out of this process. And as I mentioned, we'll see that in a minute as we go through the notebooks. The next couple of slides, again, part of the course is also eventually to have the ability to go through some of the papers. He talks about a paper that just emerged, I believe, at the time he was going through the course. And he wants to explain, once we understand the components, even if we do not understand all the code behind the components and how we get it, the interesting part is we'll be able to intuitively or conceptually grasp what is being discussed in these papers, and that itself ought to kind of motivate us to dive into the details. So again, he says, look, there is this new paper that SMA that has emerged, which says we can edit images or get images just based on textual description that we desire. So for example, we can have a target text that says a bird spreading wings. We provide a reference input image of a bird, and out comes out of the process using Stable Diffusion, a bird similar to this bird with its wings spread out, which, if you think about it, is pretty cool and quite interesting. So for example, another example input image is just that of a person with the arms exposed. You could generate from, given this input image, you could generate a person giving a thumbs up. So essentially you could create things of images of people doing things which they've never done with some reference image that you have. So this is an image of a cat, of a goat and a cat, and you could create an image of a goat jumping over a cat. And you could take a real waterfall picture, and you could create a children's drawing of a waterfall. And there are even more impressive images you can create from this single image of a dog, a sitting dog, a jumping dog, a dog playing with some toys. And with this image of a person, you could say a person with crossed arms, giving a thumbs up, giving a namaste greeting, holding a cup, blah, 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 which, if you think about it, is pretty very impressive. So how do they do that? Again, not getting into the nitty gritty of the code, but at this level, at this stage, trying to get an intuitive understanding of the process. So the iMagick process is simply a 3-step process. So in the first step, you take a target embedding, which is, if you will, and we'll again look at it, how to generate the clip embeddings in a minute. But let's say we have some process to do that. We take an image, or we take the text, a photo of a bird spreading wings, generate embedding corresponding to that. So that embedding is referred to as eTarget. We already have a pre-trained diffusion model. Okay, so this is a Stable Diffusion model, fully trained, just taken off the shelf from, say, Hugging Face and so on. So what they do in the paper is they provide this target embedding and try to get an image or corresponding to the reference image of the bird. And they just do this for a few cycles through this iteration process that I described. The paper probably covers the details of to what extent they do and so on and so forth. While those details, at least to get a conceptual understanding, aren't that important. The first thing to understand, or the simplest takeaway, is they just, if you will, train this target embedding and conceptually shift the target somewhat using the pre-trained diffusion model to be somewhat closer to this reference input image of the bird that's also provided. And so what they're trying to do by this process is get the target shifted closer. The target, remember, is just an embedding of a text, closer to correspond to this image of the bird. So conceptually, they're shifting this embedding closer to some optimal value of the embedding, which corresponds to kind of the reference bird. Then the next step they do is take this optimized embedding, lock it in place. So by that, the values of this optimized embedding now are no longer changing. In this process, this model was locked and the embedding was shifted from where it started, which is the target embedding, to some optimized embedding. Then we lock the embedding and then send it through a model where, again, this diffusion model, but in this step of the process, we allow the model parameters to be changed somewhat. Again, we don't do this for a very long time. And again, we use the reference image for this purpose. In this case, we lock the embedding and we train the parameters or fine tune the parameters of the diffusion model. So again, we don't do this for a very long time. The details are in the paper, but The first step is shifting the embedding somewhat from the target embedding to an optimized embedding. The second step is to fine tune the diffusion model.
So
and
I
the
have a
third
question.
step is, go ahead.
Sorry. So basically, for taking that target embedding, which is the embedding for a bird spreading their wings, they shift it to like a bird that's sitting on a tree or something to optimize?
It's more the way I
Or
think
in
about
the
it, and obviously,
between, yeah.
yeah, it's more of, see, this just says a photo of a bird, right? So at least what I take away, and I haven't gone through the paper myself because again, the details aren't important, or I haven't had the time to go through the specific. But the way I understood it is to say that they just, here the text just says photo of a bird. Now, eventually what we want is this bird or the image to emerge out of the process of this bird spreading its wings. So what I believe this process, the first step does is to take the target embedding, which is just words, and make it correspond to this image, but with text moving towards generating something related to this bird, right? So it's shifting, the shift conceptually is that from all the images that exist in the world or in the world of a bird that could be spreading its wings, the shift that they do is, again, I'm talking conceptually, you'll have to go through the details of the imagic process paper to understand it, but they're shifting it to correspond to something related to this bird. But that's not good enough. You then have to train the parameters of the model to also be able to generate now something corresponding to this bird. So you go through two steps. One, shift the embedding. Second, shift the model. And then the last step, combine the target embedding and this optimized embedding, some interpolated value between the two, and then use this fine-tuned diffusion model, and voila, what comes out of it or what is spit out of this is this bird spreading its wings.
So would this result in a
Now,
fine-tuned model that just knows how to spread wings on birds? I mean, or does it do other things as well? I mean, would it do other things as well?
This particular model probably will not be able to, I doubt, again, you'd have to read the paper to see whether the same model can be used to
multiple different
cause a person to spread their hands. I wouldn't think so.
Okay.
So you would probably need a fine-tuning of a model, which is why, again, if you think about it, it's not that simple, because for every image that you want to tweak, you can tweak just that image in various ways, but you can't use the same model to tweak a dog sitting and a bird spreading its wings.
Right, yeah. But maybe other birds spreading its wings, it can probably handle, but maybe not.
Yes, provided, I guess, you give a different bird, because it will still only spit out this bird, because that bird is what is being used to train this, right? So it's limited in that way, but at the same time, conceptually, the capability to modify using some reference images is pretty rad. So basically, you can put people doing things that they have never done or in places that they have never been. Right, which is pretty dangerous, but the capability nonetheless. Sorry, but there, I've been somebody else has asked the question. Is there still a question?
No, this is Lee. Sounds good.
And again, this just at a high level, as I said, I haven't, you need to read the paper. And at this stage, he just wants us to get an intuition for the steps involved, not so much the math and the details behind it.
Yeah, I'm also wondering, since this course came out in the end of 2022, is this still the state of, I mean, is it the latest ability of stable diffusion, or has it changed since then?
Oh, there have been several. I think there's tremendous progress being made all the time. I think I saw Mayank posted something where you can get stuff happening on your phone. I saw something just yesterday where I think if you provide progress is being made all the time. So, for example, to get the inference done, as I mentioned initially, as he talks about in the lectures, it was a 1,000-step process. By the time we get to these notebooks, it's a 50-step process. Who knows? Maybe now it's a 10-step process. And to give you another example of recent advance, there is a paper just published. I think somebody tweeted about it just yesterday. I didn't want to post it until we had gone through this lecture. We probably won't understand the details of it even now until we go through the rest of the course. But somebody posted that instead of using, say, 1,000 images or something to train the model to generate images with a particular person, instead of, when we say a bird here, if you want a particular bird used or a particular person used in all of the reference text that we provide, then the advances, at least the paper referred to, is one where you can have a single image of the person in your portfolio, and it will generate based off of that single image. So the point being that, yeah, there's rapid development, but again, the techniques he goes through, starting with next lecture, as Sujit begins to instruct us on, bottom up, he teaches, meaning Jeremy teaches us the basics of what the stable diffusion algorithm are, and of course, progress beyond where he taught and taking it, and all of the different advances are things that are happening even today at a very rapid pace. But if we understand the basics, then it's a lot easier to catch up on the various tweaks that are done to improve the process. So short answer, yes, a lot of development to speed up the process, to do various things with it as time has moved on. Okay, so that's where we stop with kind of theory, and we jump into the notebook and let's do it quickly. So in the interest of time, I'm not actually going to run the notebook since it takes time to run through. And I've also, as I mentioned, wanted to take you through not just the stable diffusion with diffusers notebook that Jeremy takes you through, but I also wanted to spend some time taking you through the John Whitaker's notebook, which actually gives an even better description of the components and how you can play with them. And I would really highly encourage people to play with the various parameters that we will refer to and talk about as we go through the notebooks, and do various things with it that to try and improve it, to try and get various outputs. It's a lot of fun. I haven't had time, unfortunately, as I wanted to prepare for the course and take folks to it, but I intend to do that myself as well. So in last week's lecture, we kind of went through the early part and generated this image. So I'm going to kind of skip through where we were at in the last lecture, which is generating this Jamia Howard picture in the style of a particular artist who I guess tends to use a lot of fluorescent colors and so on. But we'll start here, which is where he takes off for this lecture. So in the stable diffusion, again, you can read through it, but the various pieces, and then as I mentioned, different schedulers and what the role that the schedulers play will become clear as we go through the rest of the notebook. So in this case, what we are using are this latent diffusion images. And again, you can check this links. There are lots of links provided. You can go down all of those rabbit holes if you have the time to get into the details. But the purpose is to stick to the high level and play with these building blocks, not so much to get into the details of the code, although we'll see the first level details of the building blocks. So we already used the pipe. And here he's just extracting, if you will, Jimmy, is the VAE and pointing it to the VAE of, and the VAE, stands for variational autoencoder, and pointing to the pipes VAE. And the pipe is the process in Hugging Face that generates this inference. So we give the prompt. The prompt is portrait painting of Jamia Howard looking happy. That's what we get, or that's the aim, to get this image. But we start off with basically noise. So what he has demonstrated here is with the use of callbacks. Callbacks, again, are a way by which you kind of can get the, or save the outputs of what is being generated. And then in this case, he generates the image from that. So very quickly, there's some scaling of the latents that's happening in the code. That's important because you want to scale the latents in the same way that the model has been, the same way that the images have been scaled during the training process. That's where this magic number 0.1815 comes from. T is the time steps. Again, as I keep mentioning, there's no relation to time step, but I just think of it as steps. And the steps will correlate, as we'll see shortly, to the amount of noise that's added to the image, or the amount of noise that's extracted from the image when we're in the reference process. And I is the input image. So we take what this code does is essentially kind of save the images as part of the inference process, so that we can see the images at the various steps of the process. So the prompt is this, and the final image is, the pipe, giving the prompt, we pass in the callback, which is this latents callback, and we have 12 steps in the latents callback. So that's why you see if the overall number of steps was 60, when the callback happens every 12 steps, obviously we'll get 5 images, which is why you see these 5 images. And essentially this is just, as I mentioned, the output coming out of the unit, which is the latents. It's scaled, then passed through the VAE decoder, and then sampled. Then it's scaled because this output is in the range of -1 to 1. So you change that to be between 0 and 1, but then you want to get it onto the CPU to be able to show it, permute it in the way we want it, put it in create NumPy, and then use a NumPy pillow of the image in order to display the images. So this is what happens. What is happening here is essentially we are seeing the intermediate steps of the inference process every 12 steps. Okay. So why is the latent diffusion so fast? Because it operates in the latent space. And as we'll see in a minute, the latent space is a much more compact space of the image rather than the entire 512 by 512 by 3 image. So we begin to look into the pipeline. We load the VAE and the unit, each of which has been pre-trained. So those values have already been loaded into the model. So the VAE is the the VAE model moved on to the U. The unit is the pre-trained model again, and we move it to the GPU. What is done here is how he explains how we use the scheduler. So there are various schedulers, and the schedulers, think of the schedulers, at least at this stage of our understanding, as essentially tools which are used to add or subtract specific amount of noise that we either add or we subtract from the latent images. So this is the graph of time steps on the horizontal axis and noise added on the vertical axis. This is just a graph which plots at time step 600, what's the amount of noise? At time step 800, what's the amount of noise? At time step 1000, what's the amount of noise? And so on. And so we just use an LMS discrete scheduler. As we go to the next notebook, you'll also get a better understanding as we see some plots of the usage of the scheduler. But again, the scheduler, there are various different schedulers available off the shelf. You take them out, you create a copy of that. In this case, we are using an LMS discrete scheduler. So we have now defined the parameters. We've got the VAE, we've got the scheduler, we've got the unit, and we want a photograph of an astronaut riding a horse. That's our prompt. We say the number of inference steps is 70. As I mentioned before, this is the guidance scale. We set it at this time at 7.5. Now we look a little bit at what happens with the clip encoding process or the encoding of the text into embeddings, right? So for those who, like Sujit is an expert on the large language models and textual stuff. Essentially, this is a very simple view into what happens during text encoding. So you just take an input, tokenize it, pad it to max length. That means whatever the maximum length of this particular tokenizer is, and you get the input IDs. And what you'll see is, because this is a photograph of an astronaut riding a horse, there's only a certain number of words that get encoded. That's probably from here till 4558. After that, all the encoding is essentially all the way to the end is basically padding to match the maximum length of this particular encoder, right? And then you decode 49407, it begins to say end of text. So essentially, other than simply having these encodings, which say which pass in the relevant encoding for a photograph of an astronaut riding a horse, all of this is just padding to say it's all end of text. And then the attention mask is used to indicate what are the relevant portions when we pass in this textual prompt. So you'll see one, and the length of these will correspond to probably until about here, and the rest will all be zeros because they're all padding. Then the text encoder gives us the embeddings for the text prompt that we want, right? So what we pass in to the tokenizer is essentially the text. What comes out of it is the set of encodings that we want, and the encoding for each of the words here. So a photograph of an astronaut. So each of these is a 768 long embedding, okay, as you'll see here. And this length, the length of this guy, and you can kind of play with it to check. You can do a length and text of input IDs, and you'll find that it is 77 long. So the point is, he illustrates that we get 77 768 long embeddings. So there are 77 embeddings, and each of the embeddings is 768 wide, or if you will. So you just generate the text embeddings. As we saw very quickly when I showed you the classifier guidance, you not only pass the prompt, but you also pass null prompt. You pass not just the photograph of astronaut, you also send in empty string, and the unconditional input tokenizes that. Okay, so that again is 77 because the max length is always 77. So you get another 77 by 768 on encoding, combine them. So you just basically concat them, unconditional embeddings and text embeddings, create the latents. Now here is where it's kind of, something relevant to the discussion we were having in Slack as well, and Mayank and Sujit, it's kind of important here as to what is happening. Because we start with noise, we just generate noise in the form of the size of the input channel, the unit input channel, in the shape that we want of the latents. So the latents, as we'll see in a minute, are 64 by 64, which is, shrunk by 8 in each dimension, corresponding to the 512 by 512 by 3 eventual image we want. So we just add noise, which is what the dot.rand does. Batch size is of the batch size, unit in channels. I think in this case we use 4. So we use unit in channels of 4 and send in random noise sized or shaped in the same 5 as our latent. So this would be 4 by 64 by 64. And then we move it to the GPU. The half is essentially for half precision. And you check the latent shape. It's 1 by 4 by 64 by 64. So as he says here, the input shape is 4 by 64 by 64. After going through the unit a few times and denoising it, we'll send it through the BAE decoder, and the decoder will then decode it into a 3 to 512 by 512 image. The fact that we are actually doing the processing in the unit in the latent space is, it's called latent because we've encoded it into this smaller quantity. But again, keep in mind, this is inference. So we start with noise and emerge with the image, right? So we give it random noise of the shape of 1 by 4 by 64 by 64. After we get it through the unit, so you then say scheduler set time steps to be the number of inference steps. Remember, this was set at 70, and we do this process. Latent times the latent scheduler init noise sigma, which essentially is saying we're ready to now write the denoising loop. After having done this, we say scheduler time step. So this is where the scheduler says, okay, I'm going to take you from, let's say, if you're using 1,000 time steps, then we take from starting with 1,000 and going all the way to 0. So corresponding to this image, what it means is, since we're initially generating the max random amount of noise, because remember in inference, we start here and we want to emerge on the right. So we start with the left, which is the maximum amount of noise. So in a sense, we start at step 1,000. That's the maximum amount of noise. And then as we infer each time, our unit says, okay, this is a lot of noise. It predicts what that noise is. We subtract that noise, subtract that noise, subtract the noise. And as we go through the process, we keep adding or we keep extracting the noise, right? So the time steps are from 1,000 going down to 0. The corresponding noise values are 14 going to 0, right? So if you want
there's one thing here. So this is kind of an intuition, like if you think of in terms of physics, right? As time progresses forward, entropy increases, so noise increases, right? But because you're going backward in time, so because you're trying to denoise, you're essentially going backward in time. So that might be the intuition why time steps was introduced, the word time steps.
Or in fact, the way it was also because of the math that, the ODE used originally to solve were, kind of the Newton-Raphson method and stuff, which is an incremental iterative process. So that's viewed often as time steps. So that's where the time steps also came from. Right. So this is more a plot of the time steps versus scheduler sigmas. And you can see when the value of time steps is very high, the noise is very high, it corresponds to the exact picture shown here. So we begin to reduce during inference. Our unit predicts the noise, we subtract the noise, and we kind of keep going through. So this is what that process looks like. That's where I keep mentioning how we do the subtraction. So we take both the latents, both meaning both the coded and the null value, then send that to the model without, obviously this is an inference model, so we don't want any gradients in this process. So we just use .nograd. We predict the unit, input, time steps, encoder hidden states, which are our text embeddings from the text. So this would be the 77 by 768. We'll see in the next notebook that actually we combine positional embedding and text embeddings as is often done in if you're familiar with language models. So that happens, but it's not mentioned here for simplicity, but you'll see that in the next notebook. And we get this output from the unit and then we sample from that. That's our prediction. We get two predictions. Remember, we send in two inputs, which is one is the null input, the other is the prompt input. we extract these two inputs, and then using our guidance, where does the guidance come in or is help? This is where the guidance comes in. So what we do is you use the unconditional input, and then to that we add a scale. That's the scale that the guidance scale number provides, a difference between predicted text and the predicted unconditional. So remember that these are the two predictions. So we subtract what the predicted text, that is the output corresponding to the astronaut riding a horse or whatever that we give it, and the null input we give it, scale it by the guidance scale, and then add it to the unconditional and send this predicted value back through the scheduler step along with the time step and the latence and the previous sample. And then we get the next sample and we go through this loop a number of times. The scheduler is what is used to provide the noise that's used in this process. So that's why the scheduler is useful, or the scheduler is relevant and is important to use, or we can play with various different schedulers. And then once this process is complete and we have denoised the image by going through the 70 steps that we talked about, then, right, we get the latents, which are now the denoised representation. That is, through the scheduler, we subtract the noise, go through the process, the cycle, iteration, out comes the eventual latent. That latent is now sent in through our VA decoder, and the scaling process happens, and then we sample it. And then we go through this, -1 to 1 is shifted from that range to 0 to 1 range. Then it's permuted in order to get it in the shape that we require, converted to NumPy, detached, moved to CPU, permuted, moved to NumPy, moved to the scale of 0 to 255, treated as uint. This is all the process to convert the image from a range -1 to 1 in the shape we want it, also in the range 0 to 255, eventually display an image, and out we get astronaut riding a horse.
So in this case, the VAE decode, does it correspond to the right-hand side of the U then in the unit? I think, because if you think, it's operating on the latent.
Right hand, you mean?
Yeah. So if you think of the unit, right, it, input comes in through the left end, it goes down, from pixel space to latent space, and then goes up, from the bottom again up to the right, where it's gets you the denoised image. So if you think here, if you look at this, it says, where is this again? Var decode, where it does the sample, right? So image is,
right.
So on the bottom side, that's right. So it's taking the latent and then calling the VA decode on it. So I'm wondering, if the decode is on the, it corresponds to the right side of the unit, right? So it starts from the latent because the input is the latent, and then it goes all the way up.
The unit process continuously happens just in the latent space. Okay, it's just that, and we'll see this. It'll become even more clear, as I said, as we go through John Whitaker's notebook. The unit takes two inputs. Eventually, what emerges out of the unit is still in the latent space, but it's a denoised latent. So all the noise that you wanted to extract has been extracted over 70 steps. So what's left is the denoised latent corresponding to your prompt. That value, the denoised latent corresponding to the prompt, is still in the latent space. So it's still, size of it is 4 by 64 by 64. What you want is 3 by 512 by 512. Right. So you take the 4 by 64 by 64, send it through the decoder, out pops the 3 by 512 by 512 pixel space image. Before that, it was a 4 by 64 by 64 denoised latent corresponding to your prompt.
Okay, I'll wait till I'm still not really, but I'll wait till the other notebook. That's fine. Yeah.
Okay, so we'll go through again the
Yeah,
next
that might make it
notebook,
clearer.
and that
Yeah.
I think clarifies it
Yeah.
at least
Yeah.
to be even better than this thing does,
Srinivas,
because he's kind of hiding some stuff. Yes, go ahead, Neho.
so yeah, just following on what Sujit was saying, the variational autoencoder you think of as like a a good compression, right? So I thought too, like the left side of the unit is so you're saying the unit is
Again,
complete.
no. Sorry to interrupt, but let me clarify one thing. The VAE has the variational autoencoder, we call it, sadly, the terms might get confused, but the variational autoencoder, it's called VAE, but as we saw in the last lecture, it has two pieces. It has an encoding piece. The encoding piece is actually only used, I shouldn't say only, because you can see that at the beginning, we added the latence, we added the noise. In this case, we are in the inference process. Okay, so we don't really need to use the encoder of the VAE, because we can just shape the noise to be in the shape of the latence. That's why we don't use the encoder during the inference process, the VAE encoder. What we do in the inference process is only use the VAE decoder, because we use the decoder of the VAE to take the denoised latence, shove it through the VAE decoder, which is the decompression algorithm, if you will. As you said, the VAE encoder does two things. It can encode, and it can, using the encoder of the VAE, and it can be used to decode the image. And decoding is a decompression process. Encoding is a compression process. We did not see in this case, we didn't have to use the VAE encoder during the encoding process. Why? Because we can just take noise is noise, and shape it in the size or in the shape that we want, which is what we did here. We shaped it to the size that we wanted, which is the size of the latence.
So just to clarify, we don't need to use the encoder because the noise is already present because it's inference, right? So we just need to
the
decode
noise
it.
is, we add, in this case, we do add the noise. Here is where we add the noise. The noise is in the shape of the latence.
Okay.
We start with the noise. You see the place where I've highlighted in my notebook, in this notebook?
Yeah.
That is where we start with the noise in inference. We start with basic noise. But the noise, we don't need to encode the noise through a VAE. Why? Because we can just shape the noise. The noise is noise. You can just shape the noise in the shape of the latence. And the shape of the latence is 4 by 64 by 64, of course, that size. And that's what we have done here. Okay, we start with this, go through the unit. The unit has been trained to predict the noise. So it will predict a lot of noise, because remember, the scheduler is the one which says, okay, each time how much is the noise, and there's a lot of noise in the beginning. It will predict the noise. We subtract a certain value of the noise from the original noise, and we keep subtracting so that we subtract everything except the image that's desired. But we are still in the latent space, because this is in the latent space. The noise, we have shaped it in the shape of the latence. So we keep doing this, but what will result as a result of all this, having gone through 70 iterations, what we will be left with will still be in the shape of the latence, which is 4 by 64 by 64. But that's not what we want. We want 3 by 512 by 512. Now we need to take it through the VAE decoder, scale it, multiply the latence that are left after the denoising process, and sample. And that will give us, and of course, that will still give us in the pixel space, as as Sujit pointed out, And now we are in the pixel space, but the pixel space still needs some tweak because the pixel space is -1 to 1. When we get out of this process, we convert it and do these things in the particular cell that I'm highlighting, and out pops the actual 512 by 512 by 3 image.
I think what's happening, if you go up one, like where you have highlighted, right? Go this one here. No, not refer. Just where you had highlighted, and this one, stay here. Now go one little bit down after the graph. No, after the noise schedule. Yeah, there, this one. So here you're taking the text embedding, which is a combination of the unconditional and the two embeddings, right? That we talked about.
Yeah,
and then
that's for the classifier.
Yes, and then we are running the unit. So I think you're actually okay. So the unit is actually giving you back in pixel space, right? The pred is in pixel space.
No, in latent space. The unit is in latent space. See, remember what we're sending here are the latent.
Oh, I see. Okay, I see.
And everything is in the latent space in the unit.
Okay. So the bottom of the unit is the output.
Space.
Okay.
Yes. And so everything that the unit does and the iteration we go through is all in the latent space.
Okay.
After we are completely done with the latent space, we sample, scale, send it through the VAE decoder, sample, and out pops the pixel space image. We of course have to still, screw with it to get the desired, kind of manipulate it, if you will, to get it in the desired shape and all that. And then comes the image in the 512 by 512 by 3 pixel space. And, if it's, as I said, it will become even more clear as we go to the next notebook. But if it is not, feel free to start off the next lecture with questions and I'll be happy to answer.
Right. Yeah.
Okay, the rest of it I'm going to skip in the interest of time, because basically what he's just doing is say, okay, what I do in order to get a better understanding is just combine all the cells, put it all together and remove all the commentary I had up top. And then that enables me to get all of this in and put this all into functions. And here, just so that you don't get confused, he's just providing two inputs instead of a single input. He provides two prompts and, just generates therefore an output of two images. Okay, and then puts it all into functions so that it's easier to see in a single screen. With these three functions, you're able to completely encapsulate all the things that you are needing to happen in the inference process. So he just says, hey, I showed you all these building pieces, but you don't have to have all of this in separate cells. Just combine them, shove them into functions, and off you go. And this way you can play with it easier. It's all in a single screen that you can see. That makes the whole process easy for you to manipulate. That's all he says in the rest of that discussion. But allow me to take you through the Jono Whitaker's discussion. Again, in the interest of time and explanation, I'm not going to run it myself. I've run all of this. Would encourage you all strongly to run it yourself and stop and think through what happens during each process, which is what I think enables you to get the best understanding. So this is the notebook corresponding to lecture 9A. The person who's explaining all this is John Whitaker. Again, I think an excellent notebook that takes you through the building blocks that correspond to stable diffusion. Again, it's not every line of code that we'll go through because that will happen over time, but just to get a building block level understanding. So you install all of this, load the modules, and again, as he shows here, he is loading the VAE, right? Then he's loading the tokenizer, the encoder, the unit, the scheduler, and then moving all of them to the corresponding pieces. At least by now, you ought to be able to understand, okay, what are the components? You ought to be able to name the components, right? Which is the VAE, the unit, the textual clip encoder, the scheduler, which again, just adds or subtracts or provides the schedule by which noise is added or subtracted from the image. So what's the diffusion loop? So here, let's talk about the steps that he takes you through. So here, the prompt is a watercolor painting of an otter. The settings, this is the default height and width. Here, he's just using a number of denoising steps is 30. In the prior notebook, we saw it was 70. Here, he's just using 30. He's using a guidance scale of 7.5. As we saw in the last lecture, I think you can set it at various values. 7.5 is approximately ideal. I think at 14 is the largest value I've seen. You can play with it. The beauty of this notebook is play with these parameters in order to gain an understanding of what happens when you shift this. So you could play with and run this notebook, and I did, with this at 3, with this value, guidance scale at 3 or 1 or 7.5. What it influences, you'll see, is the result image. How closely does it correspond to the text? The higher the value, the closer it will correspond to the prompt. The lower the value, the more likely that it will shift away from the prompt that you have given it. Right? Now, these steps are essentially preparing the text. So, same steps that Jeremy took us through. We'll see a lot more of the details. He also takes us through that. Then there is this unconditional input as we saw, because that's what allows us to then combine it using the classify guidance. Remember that guidance is used to determine the scale by which the unconditional input and the textual input are subtracted. The values coming out of the unit are subtracted and then added to the unconditional input. We'll see that code in a minute again. And then you get the unconditional embeddings. You do the text embeddings. You kind of concatenate the two, set the time steps to the number of inference steps. So you tell the scheduler, hey, I want an inference process to go through 70 steps, in this case, 30 steps. Again, here you see the addition of noise. Keep in mind that the noise is added in the same shape as the latents. Therefore, the noise is added in the latent space. Move the latents to the GPU, do the noise addition to the latents. You add the initial amount of noise. Given that we are starting an inference process, this is again the most noise that we'll initially add. And then we do the same sequence process. That is, pass the two latents through, schedule the noise, get the latent input, latent model input, again, without anything, without taking the gradients, predict the noise. So this is the unit predicting the noise in the latent space. So that's why you get the latent model input. You provide the time scale, which is what tells the unit, oh, I'm in this time step. Therefore, it has an indication of the amount of noise that it needs to predict. You send it the text embeddings, which are this combined ... cat of the unconditional and the text, and then you sample. Then you split it into the unconditional and the predicted, and this is where the guidance scale is used. The higher the guidance scale, the closer your eventual prediction will be to the prompt that you provide. That's where the guidance scale comes in, and you can try, as I said, and play with 7.5 and reduce it to 1, increase it to 3, increase it to 14, and see what impact it has. And then you step through, and you go through this loop. And once you emerge out of it, you scale it, and then you send the latent through the decoder and sample. And then you do this putzing around with the image in order to get it to a pillow image. And out comes the result.
So it looks like the VAE is separate from the unit, right? So during training, then we have to train both. Right? So
In fact, that's why you also have to download the corresponding VAE with the trained. Yeah. Is this?
Yeah. And you have the unit
So
also from Conway Stable Diffusion V1.
Exactly.
1.4.
Exactly.
Okay, same.
Yeah.
So it's like a set. Okay.
Yeah, absolutely. Yeah. So now let's look at the autoencoder, right? This is where I believe you can get a much better idea of see what's happening. So because basically his two functions, pillow to latent, latent to pillow. So web pillow being just a basic image, right? So pillow to latent, no grad, latent, and Mehul is where what I was referring to applies and what you said applies, which is you encode, you transform the image, you unsqueeze it to generate this leading one, and then I, don't quite understand why he does this multiply by 2, subtract 1, but bottom line, you're encoding and scaling. So you're compressing, right? Whereas when you do the latest to pillow, you are unscaling and then decompressing. Right? So that's why I said what I said and also as Jamie explained, and as also Sudeep pointed out, original diffusion models operated completely in the pixel space. That is a cumbersome or a compute inefficient process. But once you operate in the latent space, you get, at least in the examples shared, a 48x reduction in how much compute you need to do, because it's a 4 times 64 by 64 in the latent space, and in the pixel space is 3 times 512 by 512. So if you do the math, you will be at, 3/4 of, is it 3/4 or 4/3? So I always get confused, but one of them times whatever the ratio of 512 by 64 is. And so you'll find out that you do the math on that and you'll find that it is 48 times less in terms of calculations when you operate in the latent space.
So I think one other thing that latent space buys you is the ability to influence it using text embeddings, right? I mean, if it was in pixel space, you wouldn't be able to influence it unless you had to transform both of them into some common space.
Yes, but because I'm not quite sure of that, Sujit, because the original diffusion models existed in the pixel space. They were just computationally inefficient. So you could still do what diffusion did and combine them. It was just that it required a lot more compute. So it's that part that somehow you wouldn't be able to textually influence is not right.
Okay.
You were able to do that, except that it happened in pixel space, therefore it was much more inefficient, as I understand it.
Right.
Because there was diffusion before latent diffusion. Okay, so in this case, kind of fascinating. You can just use a picture from the web, but he's now beginning to show you what are all the various things that you can play with by just playing with the components. This is really good stuff, and I'll encourage you guys, all of us, to go through that. So you just download this MacOI image. Again, it's 512 by 512 by 3. So here's what he's doing. This is where, for example, it's useful and helps you understand it even better, because now he has encoded this image into the latent space by using his pillow to latent function. Okay, and he shows you what the latents look like, because basically the latents that he has encoded is identical to the shape of the latents that we will be using in the unit. Because the unit operates in the latent space, you need to know how the unit was trained and what's the size of its latent. The size of the latent, as we saw, is 4 by 64 by 64, which is the reason that his pillow to latent function encodes it into that size. Okay, and he has a well-commented notebook, so you can go through it, and he just plots the latents, the 4 latents, and it captures a lot of information about the image, hopefully enough that we don't need to operate in the 512 by 512 by 3, but can operate in 4 by 64 by 60. And then he just takes these latents and decodes it back. And unless you have a very sharp eye, which I don't, it'll be very hard to distinguish between the VAE decoded image and the original image downloaded from the internet, because all this image had happened to it is taken through the encoder, which means compressed, and then taken through the VAE decoder again to get the input back again. but it's not exactly the same because it's kind of encoded and decoded. He says you can see some things in the eye if you look closely, but I wasn't able to detect anything. My eyesight is poor. Anyway, he just talks about all the stuff that happens here. Then he talks about the scheduler. So we'll get a little better understanding of the scheduler. So during training, as I said, and as we discussed last week, we add noise. During inference, we subtract noise. Right? So during training, we add some noise to the image, and then we have the model try to predict the noise. That's how we train the unit to always be able to predict the noise in the image. So during training, we add the noise and tell the unit predict the noise we added. So we know the ground truth noise we added, and we give that as training output and a supervised training to get the unit to be able to predict the noise we added. So if we always added a ton of noise, the model might not have much to work with. So if we only add a tiny amount, it won't be able to do much with a random starting point. So what we do is it's varied, but it's not varied randomly, it's varied according to some distribution. That distribution is what the scheduler controls, right? So the scheduler handles all of these details. For example, scheduler blah, 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 use beta start, beta end, beta schedule, scale linear, and the number of training steps 1,000. So it kind of sets up a schedule that matches the one used to train the model. So the scheduler also is something it's important to remember that if a scheduler is used, then that is used to train the model, and that's the same scheduler that's used then in the inference steps to also denoise the model. So a scheduler has to have been used in the training and in the inference of the model for us to be able to use the scheduler.
So basically,
and
the time step. Sorry. So basically, the time step is a hint to the to the model to say how much noise is present, right? That seems
exactly
to be,
exactly, which is why it doesn't exactly correspond to time as much as you can think of it as another table value, like you said, of a noise that needs to be extracted or added. In fact, it is the noise that's added, but in inference, it will be the noise that needs to be subtracted. It's what is used to train the unit to predict the amount of noise. And then, you can see the prediction of noise. Now, you can see here that he has it plotted, I should say, in the way that we use it in inference. That is, as we start off, there's a lot of noise. And then as we go through the inference process, the noise that needs to be predicted is smaller and smaller. The time steps, on the other hand, are just linear. So that's why, in fact, exactly to your point, Sujit, you just use the time step as a pointer to the amount of noise that you need to predict if you're in training, that you also predict when you're in inference, but then you subtract it from the latents. Right. So here's where he again does a good job of explaining, if you will, with this image. What you do is touch random like encoded. So what is he doing? Here the encoded is just the encoded latents, right? But he creates noise corresponding to this encoded shape. That's why the random n like, right? And then, sorry, I should set the stage. What he's doing here is, one of the things we did in the prior lecture was we also saw this example, not just of text and text embeddings resulting in desired image, but we also saw the example of image to image generation, right? Not just text to image, but image to image. So he's kind of trying to show us in the next several cells, how do we go image to image versus just text to image. So he just starts off here, and then we'll go through the detail. But here he's just showing us, okay, if you add the noise similar to the shape of the encoding, and then you do this sampling step of 10, equivalent to step 10 out of the 15 in the step above. Again, I would encourage you folks to play with this and plot this. If I were to, now obviously I'm not connected, but I've played with it, and if you change this to 0, you'll see a complete just noise in the plot below. If you change it to 15, you would see a different image. This particular image is corresponding to step 10. So step 10 is somewhere here, right? So you see a little bit of noise added. Step 10 is here. If you and by the way, if you put step 15 as I did, it's outside the range, so it will give you a range error. But if you put step 14, you'll see much more clear image of the bird, very little noise left to predict. If you put 0 here and plot, you'll see just noise. There'll be a very faint, if at all, bird outline, but most of it will be noise. Okay, let's keep going in the interest of time, and you can actually comment out and see the code for how the scheduler adds the noise. Right, so you can see the components that have all been built in, and because this is open source, you get to see the source code for it. And here's the description of how different models may be trained with different noising and different scheduling approaches. And there are, as we saw, one of the simplifications in the map of diffusion portion is saying that you can keep the variance constant across noise levels, which are called variance preserving, or you can allow the variance to vary, and in this case, it's called variance exploding. And then the scaling and how we get the model and so on and so forth. The rest, now we start to see what happens when you start from some noised version of input. So this is how we generate image to image rather than text to image. So here also we have a prompt, but as a reference image, he has provided this picture of the macaw or the parrot. Right? Maybe those are two different animals, but whatever, I believe this is a macaw, but I'm not 100%. So you use this prompt, provide the same thing. All of this code is the exact same thing. The only change we make is we say our start step, instead of being 0, which is all of the noise, is 10. Right? So correspondingly, we have shifted. We've given this prompt. We have given the image is that of, and then we say start step is 10, right? And then we take it through the remainder of this process. And then, of course, we also do the BAE decoding and see what is done. What has resulted here is the colors, if you will, have been taken from the image of the parrot and then applied to the prompt that we started off with. Right? So you can see some of the colors. So in a sense, what this image to image stuff has helped us or allowed us to do is it starts with some rough structure and color of the input image, which is that of the parrot, and feed that into your generation. And then the prompt, however, is that of the, National Geographic, whatever stuff. And so it begins to combine the structure and color of the input image, which is that of the parrot, and combine it with the prompt. And again, if you vary and by the way, I played with it too, you can vary the guidance scale on this. And the more you increase the guidance scale, it adheres to the prompt while applying the colors. If you lower the guidance scale, it goes away from the prompt and just adheres to the colors of the input image, but it's off of what prompt you give. Right, so that's what he explains here. the text. Again, I would encourage, as I keep repeating, play with this and you'll get much better intuition of what's going on and what these various knobs and settings allow you to do. And then this again is very much similar, but fascinatingly, he tells us very interesting experiments that you can do while playing with embeddings. So I'm going to skip the repetition of what we already looked at, of where the code is and how it gets generated, how the textual embeddings get generated. So you'll see that it's all 77 by 68 and so on. But the important takeaway from this is, after we have done this, we realized that after we have done the embedding, we realized that 6829 code corresponds to that of a puppy. You can see that here, and you can therefore figure out that that's that of a puppy, right? So now what he says is, well, now that we know that it is a puppy, here's just the shape. So I've already gone through a white 77 by 768. The way to grab the particular embedding is directly go to the clip text embedding and grab the embeddings. It just does in one step what we have taken multiple steps to do. Another thing you can see here is the vocabulary of the embeddings is about 50,000. That's what the 49408 shows, right? And here's the thing that we can do is we can see, he just illustrates that. So a single thing has been mapped to 768 dimensional vector, the token embedding. So puppy has a 768 wide embedding. The concept of positional embedding. So each of the 77 positions in this case will have an embedding corresponding to it, because we want to also send in the code corresponding to what position is for each of the letters or text, and then you combine them. And that's what we send in to the text encoder. Again, this is just a transformer. And the final output of this transformer block, this is what is the desired embedding that we want to get. Okay, and that's how we get the, and again, if you want to look at the code for it, you can use this, uncomment it and check the code, get the output embeddings, return the output. In this case, we are using the last layer, if you will, of the output embeddings, and then print out the shape. It's what shape of that. And here's what is an interesting thing though, a picture of a puppy, right? So you go through all that, put it through this, and you get input. But now, suppose we play with this in the in the text. So instead of a puppy, we now instead of the encoding for a puppy, he is now putting an input embedding of token 2368. So instead of, I forget now, it was instead of 6829, which is puppy, he puts in 2368. Okay, so he's now changing the particular token corresponding to or embedding corresponding to 6829. He changes it to 2368. And by doing that, what we get, and then taking it through the rest of the process to be the same, out what we get is, what he has done is change the puppy to a cat. So you can, see that the encoding 2368 is corresponding to that of a cat. So you can play with particular, so you maybe figure out the encoding of a fox, a tiger, or whatever, and provide that and see whether the image changes to that, for example. And the other fascinating thing, why is this interesting? Why go through all this trouble? Well, let's say the prompt is a skunk. Then what he does is the prompt is a picture of a puppy. But here's the thing, right? You take a puppy token embedding and you take a skunk token embedding and you say, I want half a puppy and half a skunk. So this is, I don't know, a scuppy or a punk, whatever you want to call it. And sometimes it works, he says, sometimes it doesn't. It depends on how effectively the combination image looks. But here is, you see a combination of a puppy and a skunk. So you can see how you can begin to play with these components by just changing a few things. I already saw changing the guidance scale, changing the embeddings at the embedding level, changing the combination of the embeddings. And then there's this whole concept of textual inversion, which is done. So textual inversion allows you to, it's almost like changing the style in which the image appears. Okay, and there is quite a bit of, there's apparently a famous blog. I'll post the link to the blog. I had it here somewhere. Yeah, this is the blog which describes the textual inversion paper, and he'll talk about the Hugging Face textual inversion notebook. You can look at the Hugging Face table diffusion concepts library. All of that he refers to in the notebook. So again, since we only have about 15 minutes, I'm going to rush to it, but feel free to play with these things. So this is an embedding that he is used from the stable diffusion portfolio of concepts, and basically says, I want you, the model, to use the style or the concepts that are being created by the SD concept library and provide me a mouse in the style of a puppy. But here is where he replaces the token embeddings in the embedding layer to create the verb style. Okay, and out pops this style of image, mouse in the form of a puppy. If you look at the verb style, this is what he has used to create the verb style. And you can see that the image that resulted is very much along the style of this paintings. You can play with it again to get, oil paintings and paintings in the form of particular artists and so on and so forth. And here's messing with embeddings again, mouse and a leopard, and he combines that directly in the embedding space. So text embeddings, you get it to text encoder, and then you mix them together. So you get the actual embeddings, and then you mix the embedding. So far, remember, we were changing not the embeddings themselves, but changing the text we provided to the embeddings, and then combining the text, if you will, and saying, give me an embedding which combines these two text values. But instead, you can actually directly go to the embedding space and get the expected embeddings and then just combine them. So here's a mouse, here's a leopard. Combine the mouse and the leopard, and out pops this image. Right. And then here is the CFG, which is the classify free guidance, and how changing the classify free guidance can give you, the extent of what you see here. So here he changes the guidance scale. Actually, this experiment is really helpful, at least for me. It served a really good purpose in trying to get me to better understand the process by which we start with the noise and then eventually get what we want. So I believe this video ought to be able to play. So you see this, how the extraction process is appearing. So what he has done through this is just saved the images through the callbacks and then plotted it as a video as we go through from noise to eventually generating the image, because the image that we want is oil painting of an otter in a top hat. And the steps that we go through, and then you can play with the guidance scale. And if you do the guidance scale of 0, which is what he actually inadvertently does in the video, you can see that it gives you a very different result. Of course, in this case, the guidance scale is 8, which is kind of close to the optimum, so you get a very good result. But on the left and right are the noise and the image extraction as you go through that process. And that gives you a very good understanding of process as it takes place, and also what effect changing the guidance scale has on these images. So how do we add some control to the guidance process? Here is another tweak and variation that you can play with it. Say, let's say we define a loss called the blue loss. So we say RGB. So the third value is the third value in your image is corresponding to the blue channel. So you say, I'm going to define a loss where I define the distance of the value from blue is what is my loss. And so all images in batch only the blue channel. And so you say compare oil on a canvas, 50, the guidance scale is 8. And the only change in this whole loop that you do is after you've done the noise prediction in the latent space, you add the additional guidance. And the guidance says, I'm just going to make some changes to you. Of course, pay attention to where he does it. I believe he brings it back to the pixel space, which is why he does it through the decoded range. And then, because obviously the blue loss is defined in the pixel space, not in the latent space. So then he defines the loss as blue loss of the denoised images multiplied by the blue loss scale and print out the output occasionally as you go through that. And eventually what he has achieved as a result is a blue image where, most of the image is blue. But if you change it, you remove the blue loss or you zero out the blue loss and you plot it, you'll see that the original plot is, because this is image of a campfire, has a lot of red and yellow in it. But that's not what you see when you've done the blue loss. At the low values of the blue loss scale, you'll see mostly red and orange because that's what the original image is. But as you tweak the blue loss, you'll see that the image just retains the blue. So this notebook, I think, even more than Jeremy's notebook, gives you a much better idea of the various steps, the process, the control knobs, at least at a high level that you can play with.
Mr. Nivas, can you also share the link to the article that you pointed out?
You mean the
yeah, this one.
Yeah. Yeah, sure. Yeah. And also point you to this one, which is the discussion of the progressive distillation paper walkthrough. So yeah, there's so much to go through that if you just chased every one of these rabbit holes, that alone can take you months. But I think in the interest of time and kind of staying on this path of just getting a better understanding intuitively of the concepts, I hope that was helpful. I kind of had to breeze through the latter portions, but I hope I was able to give you an overview good enough that you can now kind of go through the notebooks yourself and play with it and get
Yep, it's very helpful. Thank you. Yeah, that's great.
Any questions? And I hope this notebook gives you a better feel for the various steps and also help clarify the VAE versus UNet and what role the VAE plays and where it comes in and what the VAE encoder does and what the VAE decoder does and the latency. The UNet in a latent diffusion is always in the latent space. Inference, you add initially a lot of noise, and as long as the noise is in the shape of the latents, you really don't need a VAE encoder. But if you're starting from an image, then obviously you'll need the image and then add a lot of noise and then go through the process. But if you're training the unit, which we seldom, which we never do, because training this thing takes a lot of compute and a lot of resources. But if you're training it, then you need the VAE encode. And he kind of does show what that process is. When I say he, I mean John Whitaker. So he combines noise.
Yeah, I think it'll make, kind of, at least for me, it'll make it clearer if I can see the, the training regimen. Even, I don't have to train it, but just see it.
And I think if you go through the place where he adds noise to the image and generates the, the noised images, if you will, not just the denoised images, then you'll get an understanding of the flow of the training, which is opposite to the flow of the inference.
Right. No, that part I've seen, but he only talks at a very high level. He says, like I take random images, unsupervised, right? So I take images, I add random amounts of noise, and I make it predict the noise, right? Because I know what noise I added. But
Right.
what I was thinking is, the unit and the VAE has to be jointly trained somehow, because the VAE learns the distribution of the training images, right? So that's where I was kind of thinking. So, but I can look and see, and if I find something, I'll post it.
Any questions? Anyone else? Okay, thanks everybody for joining. And starting next week, we'll start. This is all top down, as Jamis want to do in the beginning of the lectures, just gives an overview. The first 2 lectures are that way, but next week, Sujit will start taking us through bottom up, starting with matrix multiplication. And as I mentioned before, I'm not an expert on this. I just kind of look and learn and try to go through it at a time and be able to explain stuff. And if not, we'll figure it out jointly. I don't know a lot. It will always be the case that what I don't know exceeds what I know. So don't feel hesitant to sign up in the future for leading us through portions of the course. So I would welcome all of you to sign up and take us through various sessions of the study group.
Also,
thanks everybody for joining. Go ahead, Sujit.
No, I was saying that also, even though matrix multiplication appears like really trivial, I looked through the initial parts of the notebook. There are some pieces which, like he kind of goes through things like, how do you do it in pure Python, right? And he covers things like iterators and things, maybe old hat to a lot of people here, but I thought it was quite interesting. I mean, the way he reframes the thing, right? So,
yeah, no, I always appreciate the various aspects that he covers, including in that, for example, he also talks about APL and how notationally he likes to approach it as various problems as notational problems, so you can kind of keep it simple in his head. And those kinds of tips, while not maybe directly relevant to the topic, but I find it very useful.
So that was my kind of initial take from there. So yeah, hopefully it'll be interesting.
Definitely. Okay, thanks everybody for joining. See you all next week.
All right, cool.
Thank you.
Yeah.
Bye.
Thank you.